Okay, I'm going to start recording, and if you're ready, Karan, I'll introduce you,
Sounds good.
and hopefully this is recording. I can't tell if it is.
I actually thought you were recording already when I came on, Annette. So I
thought I had paused it. Well, maybe it's still recording. Well, that's good. Okay.
Yeah, I see the recording icon, so it should be good, I
Okay.
guess.
I see it now too. Anyway, so welcome everyone. This is a combined seminar for two purposes. One is our regular seminar for the School of Nursing's T32 training grant for technology for chronic and critical illness, and it might include faculty, trainees, as well as our interdisciplinary collaborators of the Digital Health Hub, or formerly known as the eHealth Hub. And today I'd like to introduce our guest speaker, Karan Ahuja. And Karan is a sixth-year PhD student. I think this is still up to date, but you may be beyond the 6th year by now, I'm not sure. At the Human-Computer Interaction Institute in the School of Computer Science at Carnegie Mellon. He's advised by Chris Harrison and Mayank Goel. He's a scholar of the CBEL Scholar, and editor-in-chief of XRDS, formerly Crossroads, a flagship magazine of the Association for Computing Machinery, that's ACM. Karan uses his background in computer vision, signal processing, and applied machine learning to create novel sensing and interaction technologies. This has led to advancements in, if you look at his website, you'll see his image that shows the intersections of user digitization, interaction techniques, and health sensing. Today, he's agreed to present his work related to eye tracking, capturing eye tracking data from everyday devices. And as I realized I've been recording this the whole time, so we're good to go whenever you are. And I'll man the chat if you want me to, and keep you informed of people making comments or questions. So welcome.
Perfect. So yeah, thank you so much for the introduction. Great to be here. I've just shared my screen. Let me sort of share the presentation. Let me know, can you see the presentation?
Yes.
Okay, perfect. So folks, let's keep this interactive. If you have any questions at any point, just feel free to pause and unmute yourself and ask it. We can sort of we have enough time, it's an hour slot, so we can sort of go by it. Perfect. So with that, let me get started. Thanks a lot for the wonderful introduction, Annette. I'm very excited to be here to talk about my research. So as sort of Annette introduced, I use my background in human-computer interaction, signal processing, and particularly machine learning to create these novel sensing and interaction technologies. This has led to advancements in the field of perception, computational interaction, and health sensing. So in this talk particularly, you'll see the interplay between all these three together, and where people from disparate backgrounds can sort of come together to be collaborative and sort of really drive innovation along these intersections. So let's today start by defining what is eye tracking, right? Because eye tracking is this word which gets used a lot, and it has a lot of different connotations in different communities. So eye tracking can be something simply as techniques that track the center of your iris or the pupil, and which basically give you this two-dimensional point in the image space. So by that, what I mean is it will tell you the location of which your eye is on an image. You give it an image, it will tell you, okay, your eye is at this X and Y position in the image space. So that's something that people call eye-centered localization, part of eye tracking. The other are techniques that can track your gaze. That is also comes under this umbrella term of eye tracking. But basically what they mean there is not this 2D point, but this 3D gaze vector that you can see over here. And that sort of captures what you're looking at, not just where your pupil is. So that is also gaze tracking. And that is basically the term gaze tracking is used for all these approaches that track the eye, iris, pupil, and also sort of capture the gaze of a person. So if you look at the landscape of gaze tracking, different communities sort of use different terms. For example, augmented reality people sort of like to call it scene analysis. And what they really mean by that is, for example, if you imagine like AR glasses, like HoloLens or something like that, you get a first person view. That is what you would see from your eyes. And then it's very important to track what you're looking at for any amount of interaction tasks or saliency tasks or selection tasks. Then there is scene saliency, which means what is the information or perceptual density of an image, basically where people would look at in an image. So if you can imagine like a flower on a plain backdrop, the saliency would be around the flower in that case, because that would be sort of like the point in the image where people give most attention to it. So that's scene saliency. The third one in the scene sort of respective of gaze tracking is this third person view. Imagine you have an external camera that is looking at all of us, perhaps in a conference room. So that will really show that there are different people in the scene looking. So that is called the third person view of gaze tracking. And then, so that is sort of like where you're looking part. And then it is how do you look at these different parts? And that's the tracking part. So here is I've highlighted the tracking part, which is basically talks about different tracking and estimation sort of fields that gaze estimation exists in, or the different algorithms to track it. So if we go about this one by one, so there are techniques that encompasses the head pose, eye pose, and the 3D gaze vector, which in turn allows us to model things such as where the user is looking, which is in either the scene, the third person view, or even a first person view. For first person view, we can use these devices, these variable gaze tracking devices, as you can see over here, sort of like these eyeglass based form factors that have an IR emitter. They see where the pupil is and can hence capture where the person is looking onto the scene in a first person view. Then we have external trackers that are the specialized devices that can be placed maybe on a laptop or alongside a monitor, such as these Tobii eye trackers, which can capture the third person view, or basically an external camera which sees where your pupil is, where your face is, and then projects a gaze arrow into the scene along with it. And then this is where my research comes in, which is basically how do you enable it on consumer devices that are not specialized like a smartphone and other sort of like consumer devices. So to fully understand this design space of where gaze lies, let's take a look at two key dimensions of eye gaze tracking. So the first is digitization richness, which encapsulates the degree of capturing an exact and faithful representation of our eye and gaze. So we can plot some of these user digitization technologies on this abstract scale of richness granularity. You can see that a smartphone is sort of on the lower end, right? It's not that good at tracking our gaze. And then on the other hand, you have these worn eye gaze trackers that cost north of, that can even cost up to like $10,000, but are very precise in telling you where our eye gaze is, which is because the proximity of it to our eyes, right? And it's a much more constrained setting because it always moves with our face. It affords this higher fidelity. So the second dimension is user practicality. So importantly, if you look at this, practicality isn't one thing, but it's pretty multifaceted. For something or some technology to be practical, it has to be affordable, minimally invasive, and work with as few points of instrumentation as possible. Further, we want these solutions to be privacy aware and mobile, something that works in the wild, even in resource constrained settings. So you can see that a worn eye gaze tracker is very invasive, right? You have to wear something on your face and like even carry an external tracking system maybe in your pocket alongside it. Same with an external camera. But a smartphone is very practical. Most of us, almost every one of us, I can bet, on this call already has a smartphone. And it'd be great if we could just repurpose that for gaze tracking or even something like a laptop. So at a very high level, this is what you see, right? There is this inversely proportional relationship between digitization richness and user practicality. That is, all these sensors that afford this high fidelity of eye gaze capture, it's great, but are not very practical, cost around thousands of dollars. But then on the other hand, you have something like a smartphone, which sort of like is very practical, but not very rich. So this is where we want to ideally get to, right? In this top right corner, so that we can have solutions that are both rich and practical so that people can deploy it in the field and sort of make it accessible to a broader range of audience. So to build towards this, I draw on 3 pillars of strength to build towards this vision of eye gaze tracking. First, I need knowledge in human factors to understand people, how they work, and more importantly, the problems they face. Like, what are the pain points in eye gaze tracking? How should these interfaces be designed for people? I can then start building these new sensors and sensing approaches that can capture their eye gaze. Finally, I use my background in AI and ML to make sense of the captured signals, to model and derive utility from them for these human-centric tasks. So what this would enable is would take these approaches that have very practical, and what I try to do is add layers of intelligence using AI and ML, and to improve their gaze estimation accuracy, which would be the main sort of like crux of my talk today. So tracking a user's gaze on smartphone offers a potential for a very, very wide range of applications, such as portable and accessible computers, health sensing, hands-free control when our hands are occupied, for example, when we're cooking or doing some other task, and even like social interactions with eye expression. Such hands-free control can even be very important tool for building assistive technologies. Imagine someone with motor impairment who really cannot use their hands. So eye gaze tracking is a great feature in those cases to enable them to interact with the world and the technologies around them. So that's something that you can see in the first image in the left over here. So let's start by looking at geometric-based gaze tracking approaches, right? So we will start this in a chronological order as the field sort of progresses. So the field starts with geometric-based gaze tracking techniques, and most of these were very popular in the late 1990s and the early 2000s, basically. So we can start the journey by looking at techniques that first basically perform eye center localization and detection. And the technique that I'm going to talk about here is the one that uses radial mapping. So the goal of this technique is to sort of like try and capture the 2D position of the pupil in an image, or the one thing that it's highlighted over here, right? So there are different approaches to do this. There are shape-based approaches that approximate eye, sort of like try to figure out what the eye looks like, defines what an eye looks like. So you can imagine there are algorithms that says that, okay, the eye is sort of an elliptical shape or sort of has a more complex shape. There are 2 parabolas, that is the upper eyelid and the lower eyelid. And what's inside it is basically a circle within a circle. That is the iris within the pupil within the iris. And what are these? These computational models try to model this. Then there's another approach, which is more feature-based, which says that instead of just looking at the shape, you can look for distinctive features around the eye, such as the eye corners, the eyelids, and maybe even the reflections on the cornea when it's looking on the world. Then the third approach is more appearance-based, which detects eyes based on photometric appearances that are characterized not just by the shape and features, but more by the color distribution. So here, colors, textures, and all the rich geometry also come into the play. So in general, these shape-based approaches are much faster than the feature-based or appearance-based approaches because they can do a simple template matching and are very mathematically bound, so you can easily parallelize them. So let's look at how they work, right? So one way is that you can model the eye as basically as the iris and pupil as 2 separate things. So you can say that there is a darker part surrounded by a lighter part, which is almost necessarily true for people even with different eye shades and colors. And what you can do over there is you can calculate the gradient, or basically you can figure out the vectors that are going outside the eye and inside the eye. And if you have those gradients, what you can do is figure out the dot product and figure out where the dot product is 0. That is where those gradients intersect, which basically gives you the eye center location. So we do not need to exactly discuss the mathematical details, but just think about it as modeling a circle within a circle and figuring out where do you see a circle within a circle in an image and try to model that. This approach worked relatively well, ran at 60 FPS, or which is basically the modern camera capture frame rate of smartphones front-facing camera, but it still is not really used anymore in the current technologies. And the reason for that is there are a lot of errors, right? Like when it starts to look for a circle within a circle, it does not really generalize very well. So there are certain cases where due to lighting, there is errors due to the eyebrows, eyelashes, and even the eye corners, where it tries and figures out that, oh, maybe that is a circle within a circle. So over here in these images, you can see that the green circle is a ground truth where the eye is. And the blue circle is where the algorithm predicts that this is actually the eye. You can see it gets it wrong, hilariously wrong in many cases, because it's just looking at the shape and nothing else. So there are a lot of false positives. So this is where the advances in AI and ML helped in developing better features. So this is more towards 2010. And after that, people started really taking a data-driven approach to it. And sort of like the community started looking into deep learning-based approaches. So a deep learning-based approach is basically you can collect a lot of data, train a model on it, right, in a data-driven manner, train something called a neural network. And what it does is it basically helps and generalize to where the eye is, because what you have done is you've given it a lot of images of what the eye center looks like and asked it to produce what that is. So the paper I would like to talk about along this line is RGBD gaze, that is gaze tracking on smartphones with RGB and depth data. So this is, again, the latest cutting edge of research. This was published around 2 years back at a conference called International Conference on Multimodal Interaction, and basically explores how you can use current smartphones, such as an iPhone 10 or above, that have a front-facing camera and a depth camera as well, to figure out not just where the eye is, but also where the person is looking on the screen. So what we have done is we have gone from not just telling where the eye center is, but also where the person is looking on the screen, or that is the 3D gaze of a person. So most prior works in this domain use a per user calibration, which means whenever you want to use an eye tracking system, the user needs to conduct a separate session in which they provide their data to tune the model, often for each session, which is cumbersome and hinders the wide adoption of this technology. So what that calibration basically looks like is a person sort of like looks at their screen, they see a moving dot around the screen, and they follow the dot with their eyes, and using that, the model learns it. In contrast, what this approach allows is it can work right out the fly, right? Like you just take your phone out of your pocket and you can use it for gaze tracking. Like imagine like on your smartphone, if you had to train your touch screen every time you used it. Like I asked you to tap on it like 20 times, right? Like not very feasible or usable. You would just probably chuck your phone right into the trash can and not use it. So that's why you want something that is very usable. And that's where such approach comes into the picture. So additionally, you also have to achieve precise tracking, so which is often limited to the use cases in constrained scenarios, such as placing the mobile parallel to the user's head or asking the user not to move during interactions. This rigid requirement is quite different from the usual way, right? A user typically interacts with the phone, right? Like usually I'm on the go, I'm walking around, even riding public transport system, and my phone and head move a lot. So basically, it's a very challenging problem. You have two devices that move a lot, and your head also moves a lot, and you're still trying to estimate the gaze of a person or where they're trying to look at. So if you look at current approaches, this is the ARKit prediction mode. So if you imagine this is what your iPhone looks like, and ARKit is Apple's state-of-the-art gaze tracking feature. So it uses inbuilt Apple API and Apple functionality to showcase you where you're looking on the screen. And the reason you don't know about it, or perhaps have never used it, is, well, as you can see, it's very inaccurate. So this is the prediction range over here, right? This green area sort of like symbolizes what that area looks like. So it's very imprecise. You can't even sort of look at a particular icon on the UI screen and select it. It has a very large error radius, which is basically half the screen resolution over here, which is too coarse to select an app without using your head, basically. So in summary, to unlock interesting user applications on mobile devices, we need a gaze tracking system with high accuracy that works without any calibration and that is capable of running in diverse use cases on mobile devices. When we look at the development of desktop-based eye tracking, researchers have started assessing the value of depth cameras to improve the performance of RGB-based gaze tracking solutions. So what I mean by these depth cameras are the things such as Kinect or depth sensors that you can see over here in this video over here. You have this external view with cameras. There is both the RGB or the view spectrum image, and then there's a depth image, which basically tells you how far your body or each pixel is from the camera. For example, a recent study demonstrated that the addition of the depth channel could reduce the tracking error by up to 20%. The principle is that the depth map provides precise head orientation, which is the roll, yaw, and pitch of my head or the head pose, and the distance based on the screen and the head. So without a depth sensor, we need to infer such information from this RGB data alone, right? From a 2D image alone. It's very hard to figure out scale, right? Like if I tell you, or if I take a picture of a scene and ask you how far a house is, right? Or how far the moon is if I take the picture of a moon, it's very hard to say how far or close some objects are. So depth really helps resolve some of that ambiguity. And the great part about this is that recent smartphones now come with a built-in depth sensor, which is originally installed for purposes of biometric identification. So if you have an iPhone and you've seen the Face ID feature, which basically the Face ID feature works is by it has a depth camera and has an active IR LEDs. So basically what it does is it figures out how far your face is from the mobile and how far different facial features are. It figures out the depth-based geometry of your nose, your lips, even your eyes, and can then say that, okay, this is maybe Annette or this is Karan, and these are different people, and can differentiate based on the depth information. So while promising to use these mobile sensors, right, there has been no research to date that is focused on using these Face ID cameras or these depth-based cameras on smartphones. Instead, there has been a lot of research on using these desktop-grade depth cameras. So if you look at these Face ID cameras, these sensors are much more capable than what meets the eye. They are very thin, but they're also very low powered, which means that the depth map they provide is very, very coarse, right? It's not as fine-grained as the depth map something like an Azure Kinect would give you. That is something that was launched by Microsoft Kinect for gaming a long while back. Still, we can expect that even with this coarse depth sensor on smartphones could provide us enough with a rough head orientation and distance between the screen and the eyes, which would be particularly helpful in dynamic use case contexts of mobile devices. So to verify this, we first collected the first of its kind data set of RGB and depth camera-based images on mobile devices. For this data collection, we created this iOS application capable of recording and uploading gaze tracking data. The custom iOS application asked participants to look at a target, in this case, the red dot, as you can see over here, that was moving on the screen. While the user gazed at the target, the synchronized RGB image and the depth map were logged at approximately 20 Hertz. We also collected the motion data of the user measured by an IMU sensor. So an IMU sensor is basically an accelerometer and a gyroscope with a magnetometer on it as well. So you don't need to know what these things are, but basically what it captures is the acceleration, right? Or how fast an object is moving and the rotation of it. So basically it captures our phone's acceleration or how fast it moves and its rotation, basically along these different axes, which really helps us figure out how the phone moves with respect to the head. And we can use all this information together to make a much more combined and powerful gaze model. So we have this RGB image, depth data-based images, and the movement patterns of the user's phone. So as I mentioned, it is important to collect this data in diverse use contexts of mobile devices. To this aim, the data collection consisted of 4 sessions spanning 4 distinct yet common use contexts. One is standing, walking, sitting down, and lying down on a sofa instead of using the phone. So we had 50 participants involving 15 different iPhones later than iPhone 10, because those are the ones that had this depth-based camera. And out of our 50 participants, 14 of them were eyeglasses or had some kind of glasses. So we also had an algorithm that automatically removed frames with blinks. So basically, whenever the person blinks, you can imagine you can't see the eyes, so there would be a huge gaze tracking error. So you have to account for that as well. So in total, our final data set consisted of around 160,000 data points, roughly. So which is a lot of data to train sort of a deep learning model from, or like a data-driven model that can sort of take this data, figure out where the user is looking at, and train an end-to-end model or an algorithm that can predict future gaze points as well. So let me talk about the model implementation and the training protocol, which is particularly important which can give you a sense of how you can train your own models in the future. So we developed a multimodal learning-based method. So by multimodal, it just means that rather than just looking at one modality that is just an RGB image, it looks at more than one modality, such as RGB and depth image as well. So what this model does is it's used to estimate the user's gaze or where the user is looking on a smartphone. So first, what we do is we detect where the face is, right? We can figure out where the face is and get the bounding box of the face. And then using the cropped face in the RGB and depth views, we serve it as the input to our multi-input convolutional neural network. So convolutional neural networks are these networks which are amazing at figuring out embeddings or representations of images. Basically, if you've looked at the neural network deep learning hype, these features can sort of like have a sliding window, go across the whole image in patches, and can figure out what are essentially the salient parts or the important parts without having to feature engineer yourselves what those algorithms should learn, as we did in the shape-based approach that we previously saw. So in this case, you just need to give it the input and output, and the model learns automatically using these convolutional networks what are the important features to look at. So for image-based feature extractor, we made use of something called the spatial attention neural network. So spatial attention is a technique by which what you do is you learn a weighted filter on the original feature map, which basically what it tells you is what are the important parts and what are the not important parts in the image. So for an image to do eye gaze, what you can imagine is it would say that the nose is not as important to figure out where the person is looking, but the pupil is more important. Eye corners are not as important as pupil, but are more important than noses. So what it does is figures out automatically which parts of the image to pay attention at and weights them correspondingly to create an output or a prediction. So from here, let me talk about some of the results of our model. To evaluate the efficacy of model, we follow a leave one participant out protocol. So what that basically means is we had 50 participants, we train on 49 participants and test on the 50th participant. And then we do it 50 times, basically have one participant as a holdout set. So what you ideally want to do is after you do this, you even want to collect more data and run a bigger study to see how well this generalizes. So we also showcase the result for both our RGB only and our RGBD trained model. The overall result is shown on this graph. Our RGB only model had an Euclidean error, or basically the error of screen gaze from the target prediction to the ground truth. The distance between those 2 points of the target and prediction was around 2.2 centimeters, and which fell to around 1.8 centimeters on the addition of the depth data. So we can see that the depth data really helps. So we also looked at this result by different contexts and how the tracking accuracy was affected by these different contexts as well. So standing had sort of like the best accuracy among all these cases. So did sitting, as you can imagine, as there's not a lot of motion or noise introduced because of that. And the highest sources of errors were when the user was walking. That's why the user was moving around or lying down. So the reason for lying down is basically the face cropping fails because you can only see a very occluded view of the face whenever the camera is sort of like held like this. You do not get a very nice view of the user. So that's why lying had the highest error due to the least facial visibility because of this lying down context. So in addition, we also compared the system with prior mobile gaze tracking systems. To the best of my knowledge, no prior work has made use of RGB on smartphones for gaze tracking. We therefore benchmarked our approaches on two state-of-the-art algorithms that the Apple ARKit and another prior work called Eye Tracker, which are both sort of like RGB or just the view spectrum based images. So this is what it looks like pictorially. So as a result, ARKit and Eye Tracker achieve a mean Euclidean error of about 6 centimeters and 2.9 centimeters respectively. In contrast, our model that makes use of RGB and depth data offers a much more lower Euclidean error of about 1.89 centimeters. So you can see that basically this region of interest, or like how well can we detect it, is much more lower, right? Like you can now imagine dividing the screen into 8 parts rather than 2, or in this case of Eye Tracker, 3, right? But still a lot of work is to be done to get it to sort of like dividing the screen up into 16 parts and getting eye gaze to work reliably well. to use it as a pointer-based system. So that's the end goal, sort of like getting enough accuracy for one selection-based tasks. So that is, you look at a UI element, for example, this wallet app, and it opens it, or something along those lines. And then even finer accuracy would enable you to maybe even type using just your eye gaze. So we also observed that the ARKit's error becomes larger when the head is not facing parallel to the screen in situations such as lying down, or even in situations such as walking. So upon inspection, we find that our RGBD model has a very high error in some situations, such as when the eyes are partially closed or are occluded by the user's hand. For example, like when the user is sort of using the hand as well. In these cases, it is impossible to resolve a full view of both eyes, and the model falls back on head pose based gaze estimation. So basically, what we want to do is we want to be resilient to these different errors. So basically what we do is whenever we see a much higher error, we can use the previous prediction and rely on just the head gaze or just the head pose or where our head is facing to give the gaze estimate. So lastly, the great part about this is the model runs real time as an iOS application. That is, like, it can run real time on the smartphone itself, right? You do not need any additional hardware to run it, and basically offers developers with gaze tracking on the go. So for more demonstration, you can check out my website and sort of see our sort of full paper and also our full video on YouTube to see how well it works. But basically what happens over here is you can see that the crosshair is basically the ground truth that we have asked the user to follow. And the red dot is the prediction dot. You can see it works well. It lags a bit behind the prediction, but it sort of works well even when the user is sitting down, walking up the stairs, and even lying down, as you'll see on the couch over here. So as a limitation, even though our system achieves calibration-free gaze error of under 2 centimeters, the accuracy falls short of the accuracy afforded by dedicated eye trackers, such as the ones that have the desktop-based eye tracking solutions, which error is less than 0.5 centimeters. So it's 4 times less. So still, there's a lot of work to be done. But there still is some use cases in which this can still be useful. For example, if you want to select an app on the iPhone using gaze, you can still sort of do it if you sort of look at it for a while. In future, this approach can even be improved by collecting more data from a more diverse set of mobile devices and by a more diverse set of users across even more context. So that's what we have seen with these data-driven methods is if you collect more data across a myriad or a wider variety of participants, you sort of have a better gaze estimation accuracy. So this is the summary of our work. To enable future research to build on our system and contribute to the domain, we've also made our code, model, and data set freely available. Again, you can look at my website and download those as well. So most of the potential for eye gaze tracking can actually be realized once we model not just the eye gaze, but sort of the other parts of the human body along with it. So that is sort of one of the big findings of my research, right? That eye gaze alone is very useful for interfaces and interaction, but for most sensing tasks or using it for eye gaze sensing or health sensing applications, you want to digitize the whole user. And that's where the user digitization concept comes into the picture. For example, prior works have tried to model the attention deficit part of ADHD by looking at differences in fixations of children with ADHD versus those without it. In addition to fixations, a user's arm pose is very characteristic of the hyperactivity part and something that we have modeled in our work as well. So basically, if you can both model the arm pose, that gives you hyperactivity, and gaze gives you the fixation and the attention deficit part, you can see how you can have a much more holistic view and understanding of the user across both these two dimensions by treating them together rather than two disparate sort of dimensions. Similarly, ocular tremors are signs of Parkinson's that have been linked and are currently being studied as well. However, in addition to eyes in Parkinson's, there are other posture-related symptoms that need to be monitored. Thus, modeling the full body pose, in addition to eye tracking, would be very helpful if you can do that from smartphones. So going back to the smartphone example, the current smartphones have both RGB and depth cameras that we talked about, IMUs, and capacitive touchscreens, to name a few sensors. Now, all these sensors can digitize different parts of our body, as you can see here. Now we can treat the formulation of getting the user's full body pose from these digitized observations as an ill-posed inverse problem. So what I'm suggesting is rather than just doing eye gaze, why not try and recover the full body pose, but just using the smartphone itself and see how well we can do that, and maybe even use other smart devices that are on us, such as smartwatches or earbuds. For example, I wear earbuds. I also carry my smartwatch with me. Can we use all these devices to sort of give a more holistic understanding of the user? So this problem is an inverse problem, as what that means is we're trying to estimate a multi-dimensional volume, in this case, our full body pose, from these multimodal observations, which are partial and incomplete. It is further ill-posed as there are multiple solutions that could explain this observed data, and it's difficult to determine which one is correct. So we can sort of like solve it piece by piece. For example, by using the front-facing camera of the smartphone, we can capture the relative spatial position between the head and the hand holding the phone, as you can see over here, right? Imagine if I'm holding the phone in my hand. So as we do not have data for joints such as the wrist, elbow, and shoulder, we can use inverse kinematics to estimate and animate probable body poses for these joints. Simultaneously, the IMU allows us to orient the hand holding the phone, as you can see over here, right? Using the IMU, you can figure out the orientation of the hand, and based on that, using inverse kinematics, you can figure out the rest of the body joints along that kinematic arm chain. Now that the hand that is not holding the phone generally cannot be tracked except when the user touches the screen, which then allows us to estimate the finger and arm position, because now we know that the user is touching the screen in those contexts and opportunistically. So by using the phone's front-facing depth camera, we can even compute the chest normal and even the eye gaze that we talked about, which allows us to orient a user's torso independently from the head. Now we can even animate the legs, despite having no direct sensor data from below the torso. First, we can use the phone's locomotion mode prediction to load the appropriate kinematic scheme, such as figuring out whether the user is standing, running, or walking. Then by using this, we can use this information and this stride-based information to integrate absolute body movement and can coarsely animate the avatar's legs at the appropriate speed. So you can sort of see that over here, that now we can not just get eye gaze, but sort of the full body as well, albeit very coarsely, right? Like these are just approximations, but still you can have some signal to what the whole body is doing, in addition to gaze that you can use for some of the modeling tasks. So with this holistic and comprehensive representation of the user, we can enable numerous applications. Keep in mind that all these are potential applications. We have made some of these, but have not tested it out in the target population. What I want to do is sort of show you a vignette of what might be possible with this eye gaze data. So for example, for people with motor impairment in one hand, right? Like imagine if like they only have one of their hands for interaction and cannot use it, can only hold the phone, but their other hand sort of has some impairment, they can use it to control this interface by using gaze fixations along with IME-based gestures. So you can see that the person can sort of like select a UI by gazing at it and then sort of like flicking the phone left or right. This is because we both have the IMU based on the hand pose that I showed you and the eye gaze as well. So since we have depth information, the person can sort of like take it closer or move it away to do different tasks as well. In this case, the person clearly does not have a motor impairment, is using both hands, but you can sort of imagine how that would translate to those cases where a person only has one hand to use and cannot touch the screen or touch other elements. So over here is a more of a photo gallery based app where they can sort of use their face and their phone to sort of like toggle between different elements or different pictures. So wait, let me sort of like replay this one and try to show you how it works. So basically what it works is it figures out whether the user is present or not, figures out where the landmarks are, can then see that the user is looking at the scene, and then the eye gaze is enabled. And then once the user fixates on the target, we can enable the IMU-based gestures that were basically the hand pose-based gestures that we saw in the previous algorithm that could give the whole body pose. So there have also been works that have tried to make use of gaze for autism screening, but have made use of specialized hardware, right? We can now enable such techniques on consumer devices. For example, if you look at this video over here, basically all the yellow dots are for participants that sort of like have autism, and the blue dots are for the control, the yellow dots are for the control group who do not have autism, and the blue dots represent the gaze of people that have been screened for autism. This is again by some other prior work that uses specialized cameras for tracking this gaze behavior that you can see, but you can really see the difference in the gaze behavior. One is more scattered while the other is not, right? So other researchers and companies have also been working on similar techniques. For example, Apple is working on similar topics where they use their ResearchKit APIs and partnerships to sort of like collect more data and try and use their smartphone to better diagnose autism or better capture it by using children screening and looking at videos. So again, this is an active area of research, and they've mostly been using just facial models and not eye gaze, because as we saw, their eye gaze is not very accurate. So again, this is a very nice avenue for further exploration to really see how eye gaze can impact health sensing for autism. So imagine if you can go beyond gaze and also capture this holistic pose that I've talked about, along with their eye and head gaze throughout the day in many practical scenarios through the consumer devices that we already carry with us. So I think different researchers from different fields can work together to design these diagnosis support tools that supplement subjective data with interpretable, longitudinal, and objective measures of high-level contextualized visualizations, but not to like create a diagnosis tool, but sort of like create a diagnosis support tool to achieve a trustful human AI teaming in the health domain. So that is sort of one of the visions that my future work would like to work towards in a more interdisciplinary manner. So with that, I end my talk and would be happy to take any questions that you might have.
Thank you, Karan. Anyone like to start the questioning or discussion?
Really wonderful presentation. Thank you so much for coming, and I've learned a lot. I can see the applications that you were talking about in terms of sort of diagnosing where we might be able to look at tracking. What about the uses as well for sort of testing products? I'm not doing anything like that myself right now, but it strikes me that this might be the same thing you'd apply towards if you're developing an app for patients to use, seeing sort of how they're using it basically, or what they're interacting with the most.
Yeah, for sure. So for sure, you can let me sort of like pull that slide over here. So basically, once you know what the user is looking at different apps, you can imagine having a new UI or showing a new interface to a user, right? And showing them, okay, seeing what works and what doesn't work. That is for sure, Julia, something that can be enabled. Using this, you can study that's where saliency comes into the picture. Which parts are they paying attention at, which parts they are not. But again, it will be still coarse, but over time, you can imagine how you can sort of use it to estimate cognitive load. And people have sort of showed studies where they have showed basically the correlation between cognitive load and where people are looking on the screen. And then the other dimension to look at is task completion time in those scenarios. So you can imagine them, okay, can you open this app and send an email to someone and then capture their eye gaze and the time it takes for them to complete it, and sort of use both of them as sort of a model to see how good that design interface is.
Following up on that, I was thinking about the applications to usability testing and some user interface design. For example, when you have using the saliency of where people are looking, you can also sequence what they look at. And is it possible to have an outcome that's superior for task completion if they followed a certain pattern? Something like that.
Yeah, so again, something would have to be tested against the baseline of what the current technique is, right? So imagine if the goal is to sort of like send an email to someone, and you tell them the steps are you open the email app, you write out an email and send it to someone. So for that one, the system has to have the accuracy to support that as well. So for example, it would be a large application space scenario where, for example, you might find out that for email, touching is still more preferred, but for some cases such as photo selection, gaze is preferred because it's faster. But you're right. For example, like if you tell them what the steps are, the cases of error would reduce a lot. in the sense of like you tell them that, okay, if you see a large based box, you can just gaze at it and it will open up. You don't really have to touch it, because gaze really is a precursor to most of our other interaction based scenarios. I can completely imagine where you have a system where for large UI elements, you just gaze at it and it opens, but for other ones, you sort of touch it or use it in the way you currently do. You can have this gated based approach where you enable it, but for some interfaces and not for the others. But overall, because you enabled it for some, it saved time there. The overall task completion time is much less.
Okay, so one example of a real project that we're working on is to develop a clinician decision support tool for interpreting EKGs. Salah isn't on the call right now, but Karina, the GSR who's working with him is. So we were hoping to try to figure out how to present the data they need by tracking what are they looking at, and those who are most successful in making a accurate interpretation, what sequence do they follow, that sort of thing. So
gotcha.
hoping it's probably on a laptop or a desktop. And maybe it's that sort of use of data, like where they're looking, would help us design a better interface so we make things more prominent or more prioritized or something. So I don't know, are you familiar with anyone using it for something like that? Am I the only one seeing Karan might be frozen?
It's the same here. He was responding, but then I think we lost him for a minute.
Yeah, I think he was, and he got cut off. I think he might have some instability.
Looks like you're back, Karan. No?
Oh, hey, yeah.
Yeah,
sorry.
we lost you right after I asked the
second.
question.
Yes.
So
yes. So
sorry.
I think I heard most of your questions. If I understand it correctly, what you're saying is you have an expert and they're looking at some tasks, or like, for example, this EKG data. And what you want to do is figure out what they're looking at so you can mentor a non-expert to sort of like help them or guide them better in the task. Is that the...
Actually, that's a good idea.
It?
We were sort of flipping it to have naive users and how do they look at data display to help with their interpretation. But that's something to really think about, is we know how experts do it. So maybe we should learn from them and then apply it. But that's a good suggestion. Karina, you're on the call, but we haven't really thought about it that way, but makes sense, doesn't it?
Yeah, it does. There are actually some studies that have kind of broached the subject. So if I find it again, I'll send it your way.
Okay, great. I see some other questions in the chat. Yeleni said she's wondering if there are ways to detect cognitive load. It has been done in desktops via pupil dilation and or gaze time, ? Thanks for a great talk.
Yeah.
You'll probably listen to the recording to get some answers then from you.
Yeah. So basically, yes, I think there have been prior works that have estimated cognitive load based on gaze time. That is how much you are sort of like fixating on the object that the eye gaze can do. And pupil dilation, which screen gaze does not tell you, but that's where the eye center localization and some of the initial work on the image space that I talk about comes into the picture again, is that can really capture pupil dilations. But that is so fine-grained, so it's very hard to do it on consumer devices, so I must add that. And then the other one is basically task completion time has been used as a proxy for cognitive load. But a key thing to think about in all this is it needs to be personalized. It's very hard to create a generalizable model for it. For example, I might always sort of like send out or complete like a task, for example, like curating a list of the 10 my 10 restaurants out of the 10 coffee shops in my locality, right? If that's the task, I might be very fast at it, whereas someone would be characteristically slow. So that's where baselines really help, right? You have to sort of see cognitive load not just as a binary load, but it's more of cognitive load over time is something that people have had success in, or like how hard or easier the task is rather than how difficult the task is in and of itself, basically.
And Yelini, I see you're kind of coming in and out of the participant list, but if you have anything to add, or did that answer your question?
Yeah, now let me also give my email over here in case like someone else has questions, they can sort of like reach out to me
Okay.
using this email as well.
Hi, Annette. I would like to ask Karan about the autism
Mhm.
players. They were playing basketball, or
Yeah,
were you trying to see some ways of differentiating them from the other people? What was your criteria
So-
for showing us that autism? I'm interested.
yeah.
In autism.
So basically, a lot of prior work has shown that fixation maps for people with autism are different from those without it, basically on the fact that people with autism do not pay attention to most of the salient objects in the scene, but rather on the background, do not pay attention to faces of people. So the goal was, can we show people some videos or YouTube videos and try to figure out, so that's where this part comes in of like something that Annette was talking about with EKG, of where control looks at or where people without autism look at. So what you can try to see is make it an anomaly detection problem to see where if someone is not looking at those parts, then maybe they have some of those traits. So basically what we did was we recruited 25 people with autism and 25 and around 50 people without it, and measured the gaze patterns. And we saw that, in fact, yes, using a specialized eye gaze tracker, you can sort of like figure out these discrepancies that people with autism and without it do sort of like look at different parts of the image. And now the goal is that now, given that rather than using a specialized hardware, my research has shown you can do it on consumer devices, albeit more coarser, can you still figure out those differences in mobile consumer devices as well? So that would be a very interesting area of research.
Yeah, and maybe develop some criteria,
Exactly. Yeah. Yeah, precisely.
Thank you.
Yep. So again, if that's something that interests you or you have more questions, feel free to reach out to me. I'm also like on the faculty job market. So I'm going to be starting my new role as a faculty. Hopefully I'll decide by the end of the summer there. So yep, definitely a very interesting time to build these collaborations as well for me as well.
Congratulations.
That's, do you hope to stay in the Pittsburgh area, or you have a broad?
So I have no, I don't think it'll be in most of the school. I didn't apply to CMU. So most of the school are either in the Massachusetts area, 1 or 2 in Switzerland. So let's see.
Okay.
Very
All right.
close.
Well, you'll have to keep in touch. Anyone else have any other questions
sure.
right now? But thank you for your email address, and each of us can follow up if needed, and vice
For
versa.
sure.
If you want to reach any of us, you can contact me and I can go from there. But thank you
For
so
sure.
much for your time. This was a lot of information, but very digestible. Thank you for your presentation.
For sure. It was my pleasure. Thank you so much,
Okay.
folks.
Take care.
Take care. Bye.
Just to check, Annette, is the
Yeah.
next meeting kind of end of year wrap up, or do we have another presenter coming at that point?
Next week is the, I'm trying to stop the recording. For some reason, I can't stop it. Let me go here, record. Oh, shoot. Okay, anyway, next week we have a guest coming to the hub meeting.
Mm-hmm.
Dr. Bond from Germany is giving a general HCII talk,
Mm-hmm.
but then we won't have any more T32s until May 18th when Dean Casper comes to join us.
Yes, I actually, what I was asking, I think I'm missing next week's hub meeting because I'll be at the Society of Behavioral Medicine conference. So I'm sorry about that. But no, I was more asking about the meeting